Hello, today we're going to learn about Markov Chain Monte Carlo, which in short is also known as MCMC. There are many variations of MCMC, and today I'm going to focus on the Metropolis Hastings algorithm one step at a time. Let's start with an example. In every model, there are variables and parameters. Variables are quantities that vary in the study. Here they are yt, yt minus 1, ut, and random noises t, and random noises are drawn independently from normal distribution. Parameters are the constants. Here they are beta, alpha, u bar, mean of random noises, which is 0, and sigma. If somebody provides us with the data on ut and yt minus 1, then we can predict yt. But only if we know the parameter. The issue is the parameters are usually unknown. In our case, 4 out of the 5 parameters are unknown. Now, what Metropolis Hastings algorithm can do are estimate the parameters and provide the full posterior distribution of the parameter estimate. Let's use Metropolis Hastings algorithm to estimate the unknown parameters. Actually, we will focus only on beta. Once we understand how the algorithm works, we will estimate all of beta, alpha, u bar, and sigma in part 2 of the video. For now, plug in any numbers. For alpha, we assign negative 0.2. For u bar, we assign 5. For sigma, we assign 0.01. Let's go through the algorithm step by step. The first half of the algorithm are what we call pre-processing steps, which means setting up the initial conditions and the equations. The bottom half is what we call the updating steps, which means repeatedly updating the initial values to find the final parameter. This section is what referred to as Metropolis Hastings algorithm. But before we go here, we must first set up the initial conditions and equations. First, provide an initial guess of beta. This value can be anything because we just need to give something to the algorithm to improve upon. But it is better to make an informed guess so that there is a higher chance of finding the correct estimate and finding it faster. For example, if the parameter is a standard deviation, then we know it is positive, so we should plug in positive number. In our case, beta is an autoregressive parameter, and theory tells us that it should be between negative 1 and 1. Additionally, let's say from past observations in the field that we are researching about, we know that beta should be positive. So beta is between 0 and 1. For now, we will set beta to be 0.5. We'll make a table so that we don't forget. The second thing is to guess the probability distribution of beta. What it means is that we have a belief about the uncertainty of beta, and we should make it explicit. For example, here is our belief structure about beta. On the y-axis is the probability density, which indicates how probable a value being the true value of beta. On the x-axis is the various possible values of beta. We think that the most likely value for beta is 0.5, so we assign it with the highest probability density. But we are not too sure, it could also be 0.6, so we assign some probability density. 0.1 could be true too, but unlikely. In any case, we are sure that beta cannot be below 0 or above 1, so there is 0 probability density in these regions. So that's the idea of assigning prior distribution. In practice, we do not have to construct the distribution ourselves because there are already plenty of established distributions out there. Normal distribution, uniform distribution, beta distribution, and these are just to name a few. So the first step for us is to choose the right type of distribution. The key ones are usually normal distribution, which has the key property of taking parameter of any values from negative infinity to infinity, and the probability distribution is symmetrical. Uniform distribution has the key property of assigning equal probability density for any numbers in an interval. So this would be a good distribution to choose from if we are not too sure about our prior. Beta distribution has the key property that it takes the parameter values from 0 and 1. This distribution is bounded, unlike normal distribution. Gamma or inverse gamma distribution has the key property of it taking parameter values from 0 to infinity. Now, in our case, we know that beta is between 0 and 1, so beta distribution is the right choice. The second step is to choose the right shape from our distribution. Pick the shape that is most closely aligned with our prior belief. For example, the shape of beta distribution is determined by two parameters, and if we set parameter 1 to be 1 and parameter 2 to be 6, this will be the resulting shape. And if we set the parameters to be both 100, then this will be the shape. And if we set the parameters to be 5 both, then this will be the shape. Since this looks quite aligned with our prior belief, we will select beta 5 and 5 as our prior distribution. In later step, we will iterate over different values of beta. For example, when beta is 0.5, the probability density is 2.46. Here is when beta is larger and smaller. We will refer to the probability density under this distribution at h beta as beta 5 5. Step 3 is figuring out the likelihood function. Now we know from Bayes' theorem that posterior distribution is proportional to the likelihood times prior distribution. Our goal is to estimate the posterior distribution. We already have prior distribution, so if we can figure out the likelihood, then we are almost there. Likelihood captures how well our guesses of beta explain the observed data. Let's take a look at our model. If we bring this part to the left, then we are left with random noises on the right. Because random noises are normally distributed with mean 0 and standard deviation 0.01, we can replace the right hand side. This equation forms the basis of likelihood function because if we plug in observed data for yt minus 1 and ut, and we iterate over different values of beta, then we can find the value of beta that best explain the observed data. The good thing about being normally distributed is that it has well-established formula which helps us to check which value of beta best explains the observed data. Here is the general formula for normal distribution, and here is our model. Let's plug in our model into the formula. So here is the formula. Our objective is to check which values of beta best explains the observed data. So first let's collect data on yt minus 1 and ut, and once we have the data, we can iterate over different values of beta. The formula will give the likelihood. The higher the likelihood, the better is beta at explaining the observed data. And because we will go through different values of beta, we will append this symbol in the formula. For example, like this, which means we are checking the likelihood when beta is 0.5, or like this when we are checking the likelihood when beta is 0.9, or like this when checking beta is 0.4, and so on. For now, we will stick with beta being 0.5 because it is our prior. Now we need to collect data. Here is the data on yt minus 1 and ut for 200 time period. So now we can start computing the likelihood for each time period when beta is 0.5. Let's position the formula to be larger so we can see better. Plug in these values into the formula and we know what the coefficient is, so we obtain the likelihood. Repeat for all time periods. Note that for period 1, the likelihood is empty because during this period, the data for yt minus 1 is empty. Now we have likelihood for individual time periods. The likelihood tells us how well is beta at 0.5 at explaining the observed data at each time period. But what we want is the joint likelihood. What it means is that instead of individual likelihoods, we want all these periods combined into one likelihood. And theory tells us that if each of these is independent, the joint distribution is equal to the product of their individual likelihood. Indeed, they are independent because if we look at our original equation, then we know that the first term is just random noises at time t2, the second term is random noises at time t3, and the last term is random noises at time t200. And we have already assumed that random noises are independent. So we have our likelihood function, which is the multiplication of likelihood at each time period. Now if we substitute in the formula, this is what it looks like. Actually, it is easier to work with log scale because we can add these terms rather than multiply them. Taking log will give us additive terms, so we are done with this step. This is our log likelihood for beta 0.5. We will call it log likelihood beta 0.5. When we iterate over different values of beta later, we simply replace beta in the equation from 0.5 to 0.7 to 0.3 to 0.5 and so on. So we are done with steps 1, 2, 3. We have 6 steps to go. Step 4 is an optional step to optimize our prior. The idea is that from our prior 0.5, we optimize it using numerical techniques, and then use the optimized prior to initiate Metropolis Hastings algorithm. Technically, this step is not really part of Metropolis Hastings algorithm, but it speeds up the process of finding the right beta estimate, and it becomes important as we deal with more complex models and more unknown parameters. In part 2, we will look into using this optimized prior to find all of the unknown parameters. For now, we will skip this step. Number 5 is to set our current beta value. This simply means setting beta to be equal to our prior, which is 0.5, and fill our table. Step 6 is to propose new beta. We do this by taking the current beta times a term consisting of scaling factor, covariance, and normal distribution with mean 0 and standard deviation 1. Now, we already have current beta. Normal distribution is also available to us. This can be easily generated in most programming languages. Scaling factor is a number that scales up or down the random number. What it will affect is the acceptance and rejection, which we will see in step 8 and step 9. So we will revisit this scaling factor at the end of our algorithm. So for now, set scaling factor to be 0.01. Covariance is a term that captures the variance of our estimates of beta, which means their uncertainty. Or if you are estimating more than one parameters, this term also captures the covariance between the different parameter estimates. For now, we will set it manually at 0.01. In part 2, we will look into deriving the covariance mathematically. So now let's calculate the proposed beta. We have our current beta to be 0.5, scaling factor to be 0.01, covariance to be 0.01, and we will use Python to generate random number. Here's how we do it in Python. So here is our proposed parameter, which is 0.504. The next step is to calculate the posterior probability density of our proposed and current beta. We will use Bayes' theorem. Posterior is proportional to the likelihood times prior. Also, working with log scale is easier, so let's log the expression. Now, we already knew these two terms, log prior and log likelihood. Now we want to calculate the posterior probability density for current beta and proposed beta. So we will just replace the value into the formula. So here are our log posterior density for current beta and proposed beta. The next step is to calculate the acceptance ratio. We do this by taking the ratio of the probability density of proposed beta over current beta. Since we use log scale, let's transform this formula. We will plug in the values and we get 171 as the log acceptance ratio. Now decide whether to accept or reject the proposed beta. If acceptance ratio is larger than 1 or in log scale larger than 0, then accept the proposed beta and set the current beta to be proposed beta. In our case, the log acceptance ratio is larger than 0, so we accept the proposed beta and we set the current beta to be the proposed beta. Now, if the log acceptance ratio is less than 0, it doesn't necessarily mean that we reject the proposed beta. Instead, we draw a random number from a uniform distribution between 0 and 1. And if acceptance ratio is larger than the random number, but actually let's change everything to log scale. If log acceptance ratio is above the log random number, we accept the proposed beta and set current beta to be the proposed beta. Otherwise, we will reject the proposed beta and retain the current beta. So we are done with iteration 1. So let's store the result to another table and we iterate the procedure in iteration 2. and repeat in iteration 3. Each time store the outcomes, and so on for thousands or millions of iterations. Let's do 100 iterations. Here we first consider the prior 0.5. After iteration 1, the proposed value is 0.5044, which is accepted, so we set the current parameter to be the proposed parameter. Since we have no rejection yet, so the acceptance rate is 100%. Plot the current parameter for iteration 1 here. The x-axis is the number of iterations. The y-axis is the current parameter. We will also record the histogram of the current parameter here. Since there is only one instance of 0.5044, the count is 1. In iteration 2, the proposed value is 0.5039, which is rejected. We retain the current value of 0.5044. After 2 iterations, there is one acceptance and one rejection, so the acceptance rate is 50%. We plot the value of second iteration here, which is a horizontal line because the value remains unchanged. The number of instances of 0.5044 rises to 2, so we update the histogram. In the third iteration, the proposed value of 0.5175 is accepted. So there are 2 acceptances in 3 iterations, equivalent to 66.67% acceptance rate, and we plot the value for the third iteration here, and we update the histogram. In the fourth iteration, the proposed value of 0.5253 is accepted, and the plots of both diagrams are updated. Let's see what happens after 100 iterations. Here we notice that the parameter values at first are wandering, which happens because the algorithm is searching for the optimal values. They begin to stabilize after a while, hovering around the optimal value. We are interested in the posterior distribution. This initial wandering phase, meanwhile, can contribute to inaccurate distribution of our parameter. So usually we will discard the first few thousands of the iterations when constructing the histogram. These first few thousand iterations which are discarded are called burn-in period. So let's repeat this iteration for 50,000 times and use the first 10,000 period as burn-in. At last, we have gotten what we set to achieve, which is the posterior distribution of beta. The final estimate of beta is usually calculated as the mean of this distribution, which in this case is 0.7018. Since we have the full posterior distribution, it means we can find the uncertainty too. For example, what is the 95% credible interval? From our parameter values post burn-in, order them from the smallest to the largest. We have a total of 40,000 samples after discarding burn-in, and find the 2.5 and 97.5 percentile. This is the 2.5 percentile, and this is the 97.5 percentile. This is our credible interval. In this example, the credible interval is between 0.6974 and 0.7062. Or we want to know what is the probability that the true value of beta lies between 0.695 and 0.7. In this case, we will calculate the proportion of our samples that lies between these values. So we are done with estimating beta value and distribution. The last part of this video is to do some diagnostic to make sure that what we are doing is correct. The first thing is, what is the acceptance rate? As a rule of thumb, we want it to be between 20 to 40% or even 50%, which indicates a healthy coverage of parameter values being explored. In our example, the acceptance rate is 27.1%. Let's see what happens if we increase the scaling factor, which is currently 0.01 to 100. So we see that the proposal step is too large, leading to too many rejections. The acceptance rate is only 0.27%. As a result, many parameter values are overlooked when constructing the posterior distribution. Let's see what happens if we lower the scaling factor to 0.000001. The acceptance rate is large at 95.1%, but we see that the parameter values are moving slowly. As a result, after 50,000 iterations, not as wide range of parameter values as it could have been explored. This is inefficient. Secondly, what is the autocorrelation of the 40,000 drawn parameters values after the burn-in? As a rule of thumb, we don't want them to be autocorrelated. This is the autocorrelation with scaling factor 0.001. This is the autocorrelation with scaling factor 0.000001, and this is the autocorrelation with scaling factor 100. Here, the parameter values are not as correlated, which means the drawn samples are more independent of the previous ones. As a result, the parameters values are explored more efficiently, providing a good approximation of the true posterior distribution. Here, the parameter values are highly correlated, which means the drawn samples are more dependent of the previous one. Because of this dependence, the parameter values move slowly. More iterations may be required to thoroughly explore the possible parameter values and provide reliable approximation of the posterior distribution. Recap what we did. First, we provide a guess of beta, which we call prior. This is 0.5. Second, we provide a guess of beta distribution, which we call prior distribution. We choose beta 5. Third, we figure out the likelihood function. Fourth, we initiate the current value of beta for Metropolis Hastings algorithm, which is equal to our prior, which is 0.5. Fifth, we propose new beta by taking the current beta times a term consisting of the scaling factor, covariance, and normal distribution of mean 0 and standard deviation 1. We manually set the scaling factor and the covariance to be 0.01 and later check the diagnostic at the end of the algorithm to make sure that everything goes well. 6. We'll calculate the log posterior probability density of the current and proposed beta using Bayes' theorem. 7th, we calculate the log acceptance ratio. 8th, accept or reject the proposed beta. 9th, repeat the steps for 50,000 times, discarding the first 10,000 as burn-in. And 10th, we check the acceptance rate and the autocorrelation to make sure that everything goes well.